Okay, so hi everyone, Sean Muller again from Electronic Engineering at IT Sligo. Now this will be quite a short little lecture segment, and it's on a thing called groups, which are a mathematical just a mathematical feature that we're going to go through. I could quite easily just drop this from the course, and there were a number of things that I looked at as regards will I just cancel, and this is one of them that's close to it, but I'm going to go through it relatively quickly. I'm sure if you looked at it first, it looks kind of like a wall of mathematics, but really the whole point of this is just that you will sometimes come across these different ideas, and I just want to give you an idea of what they are, because oftentimes it can just you could be reading something and it'll mention one of these things and it completely throws you, or you think this is completely impossible to understand, whereas in actual fact it's just really a fairly simple idea that you then just have to follow all the way down to see, well, which category are you in. Okay, so that's all it is. A few acknowledgements to start off with. Now, anything in tonight's lecture, particularly what's coming in this one and the one following, it's worth your while looking at Daniel Kremer's, I think it's, I don't know, is that Kramer's or Kremer's? He's from the Technological University of Munich, and he has all his multi-view geometry computer vision lectures up on YouTube. Well worth a look there. He does quite a lot that's similar to what I'm doing here, and I've taken quite a lot of information and inspiration from his stuff. He uses that book, this book here, An Invitation to 3D Vision, as the textbook that he kind of follows. So again, if you're watching his stuff or watching some of mine and you want to go a little bit further into it, you can find that book there. Once again, the main textbook here, the Richard Zalewski computer vision textbook, is very useful for seeing some of these ideas just on a single page and maybe a slightly different version of explanation of it. But these are basically just mathematical ideas. How many people have come across this mathematical idea of a group? It's a number theory idea. Is anybody saying yes or no to that? A group? Have you come across it? No. Patrick has. Okay. Oh yeah, Patrick, you probably would have in some of your PhD work. Okay, so no. So I'll just maybe give you the general idea of it here, and it's not vitally important, as I said, but it just might make some other things a little bit easier to kind of swallow if you know that it's really just a formal set of rules. Almost everything we do in maths is just a formal set of rules that has a scaffolding, and we start with what we call axioms, which are things that are self-evident and we don't have to explain, and we try and start with this. I don't know why I'm saying we, I don't do much of this, I'm not really a mathematician, but they, shall I say, they start with a set of these kind of self-evident truths. They try to start with as few of those as they can, because they can't necessarily give a full proof for those things. And what they try and do is build everything else within maths up from that small set of rules, and build everything on top of everything on top of everything. So if you've ever looked at any of these proofs and theorems, they normally have to use some other theorem, and it's a matter of just following it all the way down to see that the proof is all there, and that it's all built on a proper structure or scaffolding. So groups are just one of those things where we have a particular set of rules associated with them. So certain sets of linear transformations, so we're talking about linear transformations here, so linear algebra and so on, form what we call a group. And a group is a set G, so we've got some set of numbers or vectors or whatever it might be, and there's an operation associated with them, and that operation could be plus, subtraction, so addition, subtraction, division, multiplication, convolution, any of these ones. So we've just shown it as some operation there. I've just shown it as a little O, whereby that if I take two items from that set and do this operation on them, I end up back with another item that's in that set. I don't fall outside of that set to somewhere else. Okay? When we see some examples, this might be a little bit more obvious as to what we're talking about. So, for example, if I do the operation on two of these things, I end up as another element of that set, and that happens for all elements of that set. It's not just that this happens to some special ones within it, it happens to all of them, and this is required for it to be called a group. Okay? The second thing that's required is this associative law, which I'm sure you've seen many times in other things, which is just to do with if we're putting three operations together, whether we do two of them, which two we do first, and then the third one, and how we move about with those things. Now, be careful. This is not the same as the commutative law, whereby if I take two numbers x and I multiply that by y, that's the same as multiplying y by x. That's not the same as the associative law here, and you'll notice that we don't have the commutative law here, so this is not necessarily required for these groups, but obviously if you have that as well, it's another great thing, but it's not necessarily a requirement for something to be a group, that commutative thing. So what this also states is that this guy here, okay, that stands for there exists. Okay, so what it's saying is somewhere, somehow, there exists this thing. Okay, that's all that means. And it's saying that there exists this thing called little e here. And it's one of the elements of our set. And it just so happens that this particular special little e thing, if I do the operation with any element of the set, okay, so for all elements of the set is what that means, what I'll end up with is back with the exact same element of the set. So this is sometimes called neutral, or also called the identity for some of these things. So if you take something like addition, and what is the neutral element for addition? Well, if I have x plus 0, I'll maybe write that the other way around. I'll say 0 plus x just so that you see it there. It's the same as that. This is our e here for addition. Okay, and I end up with x again. And that's all that's saying. So what it's saying is that for us to have a group, there needs to be some element of that set that acts as this job here, okay, and for multiplication that would be a 1. So there has to be an element of the set that will actually fulfill that job, otherwise you have something but you don't have a group, okay. And the other one then is that there exists an element of the group that is an inverse of every other element of the group. Okay, so every element in the group has an inverse, has something that's the opposite of it, so that when we do this operation, whatever the operation is, we get back to this e thing, get back to the identity. Okay, so for addition again, if I have x, what's the opposite of x? It's minus x, and I end up with 0, which was my e thing. Okay, so this is just a formal set of rules, and it's saying if you've got a set of something, vectors usually for us in this particular case, if you've got a set of vectors and you can it obeys all these rules always, and that's what maths is built on, it's these rules. If it obeys all these rules always, then you've got yourself a group. Is that good? Is it bad? Well, that comes later, but generally speaking it's good, because it means then that once we know, or we can prove that we have a group, we can use that for all sorts of other things as well. Leo Creedon, who's your maths lecturer, would be able to tell you an awful lot more about this. He probably doesn't necessarily cover it in the subjects he's doing with you, but this is really a big part of his area, which is group theory and group algebras and so on. Okay, so he'd know a lot more about it than I would. But that's just a formal set of rules. Now what I'm going to mention to you is a number of groups then, and the reason I want to mention these to you is that there's a chance that you will come across these in literature from time to time and go, what in the hell is that? And just for you to know that actually, whether either you end up with a situation where it's vitally important for you to know, or you realize, yeah, that's just that formalism there, and they're just stating it as a fact. Okay, so an example here would be square matrices. Okay, so 4x4, 3x3 matrices, and this exists for any type of square matrix. If the matrix is real, okay, in other words, doesn't have imaginary numbers in it. If it's non-singular, which means it's invertible. Have you come across that term singular and non-singular in terms of matrices? Have you used that terminology? Okay, so you are familiar with that. Okay, so if we've got a square matrix and it's invertible, okay, this forms a group. Okay, so in other words, it has all of the attributes that are required for a group with respect to matrix multiplication. So if we go back to here now, what we're saying is that this is a group with regards to matrix multiplication. So now I can replace all my O's there with multiplications, specifically matrix multiplications. Okay, now if you remember, what's the thing about matrix multiplication? If I have A, and that's a square matrix, by B, is that the same as B by A? Okay, so we're getting mostly no's there, thankfully. Okay, so even if they're square matrices, this is not commutative. Okay, this is, or it might be. I mean, it could happen accidentally, but it's not guaranteed to be commutative, and in most likely won't be. Okay, so even with square matrices, it does matter. But remember, that wasn't one of our rules. Okay, so we're not saying that square matrices, if they're invertible, that we can commute them in this way. All we're saying is that it obeys all the other rules that we have there, which means that it has an inverse. And does anyone know what the E would be? What would be the member? What would be the member of the square matrices? Let's say a 3x3 square matrix, for example. What would be the little E here for the invertible matrices? What do you reckon that would be? Can anyone guess what it would look like? Nobody's jumping for it. Okay, so it's the identity matrix. And if you multiply any square invertible matrix by that, yeah. I mean, it's there are other bases though that would there are other bases other than this. This does happen to form a basis, but that doesn't answer the full question. So the identity matrix is the only element, and as you can see, that is a square matrix. So it's a member of the group. If we multiply it by any other member of the group, we get that member of the group back. Okay, and also if we have a member of the group which also has an inverse, and we said they're invertible, the invertible matrix will also be a 3x3, or sorry, will also be a square matrix. If you multiply those two by each other, you will be back at this identity matrix. So again, it follows that set of rules there. Okay. So this group is called the general linear group, GL, and N stands for the size of it. So for example, if we're dealing with 3x3 matrices, the N value would be 3 there. That's separate from the group of 4x4 matrices. Okay, so each one of these separately forms a group, and it will land back inside it. Okay, so it consists of all A in Mn, which M just rather than an M by N, which have a determinant not equal to 0. Why would having a determinant equal to 0 be a problem? Why do you think that would be a problem? Having a square matrix with a determinant equal to 0. Yeah, so your issue here is that it's not invertible, and you can say that in lots of different ways, but it doesn't it doesn't have an inverse. And Patrick is saying it's like a division by 0. In other words, that if you end up doing some transformation that puts you to 0, you can't work your way back. It's like dividing back by 0. You can't get your way back. Okay, so clearly that is not part of the group. So that's fine. So it's all the square matrices that don't have a determinant 0. They're the ones that are good. There's a subgroup within that group, and they're like a clique. Okay, so basically if you do these operations on this subgroup, they stay within their subgroup. Okay, but as it so happens, they're also all inside this larger group, and that's called the special linear group, and they are the group that has a determinant of +1. If you have a determinant of +1, then you have a situation whereby if you have a square matrix, it has a determinant of +1, and you multiply it by another square matrix that has a determinant of +1, you will end up with a third square matrix that has a determinant of +1. And all the other rules, multiplying it by the identity and all that, they all will operate in the same way. Now, why is that useful? Can you think of any matrices that we've come across that have a determinant of +1? I mentioned some of them in the last lecture. No, go on. Yeah, the rotations, exactly, which are the orthogonal matrices, which are, have a have all eigenvalues of 1. They'll have, if you multiply all those eigenvalues together, you'll get 1. They have a determinant of 1, which is like having a volume of 1. And so they don't affect anything that occurs to them. So yes, again, and this is known as the special linear group. So there's a bigger group called the general linear group. Inside that, there's a special linear group which has certain things. And this is very, very useful because once we know that something's in that group, we already can take all of the knowledge. It's like taking a software library. We can already take all of the things that work with that everybody has figured out about the properties of that group, and we can use that to our advantage in different manipulations that we do. So the inverse of A is also in the group. The determinant, yeah. What's the case with that? So if I have an orthogonal matrix that is a determinant of 1, then its inverse must have a determinant of 1 divided by 1, which is of course going to be 1. So again, the determinant of A inverse is the inverse of the determinant of A. That's perfectly fine. So it stays within that group. Okay. And what that basically means is if I rotate something, there's a rotation that I can do to rotate me back, and nothing will have changed in between. Okay. So there are two names of two groups. Groups can be represented by a matrix. So we can actually represent the group itself by a matrix. So for example, the set of rotations form a group. So rotations are a set G that are attached to the linear group there, as we can see, the Ln. Now, the rotation, a zero rotation. So imagine we rotate, but I tell you to rotate something, but I tell you not, to rotate it by 0. What happens? Well, we just sit still. We don't move at all. That's a rotation matrix that's given by the identity matrix. In other words, don't rotate at all. And we can also we can do the associative thing there, where we basically my iPad has suddenly decided to tell me all the podcasts that are going on. So move along there, guys. Okay. We also have the fact that if we do an operation on two of the vectors there, such as multiplication, and then we do a rotation on it, that's also the same as rotating each of them separately and then multiplying them. Okay. So such a map or is called a group homomorphism. Again, that's really just for, it's not really something I'm going to be saying much, but if you come across that term, just so that you're aware of where it comes from and what it is. Okay, so there's an affine group, and we've seen this term previously. Now, the affine group is basically if we have a transformation L which goes from Rn to Rn. Okay, now remember, this is just mathematical formalism. So imagine that I've got a vector with 3 elements here, x, y, and z, and I do a transformation on it that ends me with x1, y1, and z1, or something like that. Then, in other words, that I move from that to that. So then in that case, my n would be a value of 3. So that's all that means. It looks complex, but it's not saying anything more than that. So if this is defined by a matrix A, which is in the general linear group, and by a vector B, which is just in Rn, and remember that we do our rotations in the general, we've the ones there they're in the special linear group. We'll come back to that in a moment. And then we do a translation, which is not the same thing. It has a separate vector associated with it. Then we describe that as this. We have the matrix acting on X and then adding a B to it. Okay, so this is not a linear thing. It's an affine, what we call affine. If B was set to 0, then basically all we have is just AX, which is a linear operation. Okay. Now, what we can do, again, with these marvelous homogeneous coordinates is that we can introduce the homogeneous coordinates here like we've done. So instead of 3, we would introduce it, we would add a 1 to it to make it a 4. And we can then have a linear mapping. So what we do is we take our x, y, and z and add a 1 onto the end of it. Okay. So we add a 1 on there. Right, same as that. We'd add a 1 on here. And what that allows us to do is to put the matrix in this form, A. Then we've our B there separately, okay, and we set it up like this. And if we do this multiplication, you can see what will happen we will multiply the A by the X and add to that the B multiplied by the 1, so that gives us AX plus B. And then the 0 multiplied by the X gives us 0 plus 1 by 1, which gives us 1. So again, we end up with this homogeneous coordinate at the end of it. Okay. So this is this affine one is in the general linear group, and B is in Rn, which is called an affine matrix. Okay. Now bear in mind, we didn't say that this was in the special linear group, so we haven't guaranteed here that we will have that this A here would have a determined 1 or anything like this. This could make it bigger or smaller or anything like that. So it's in, we call this in the general linear group n plus 1. So we make ourselves one dimension bigger in order to do that. So the affine matrices form a subgroup, of the general linear group of GL n plus 1. This is a bigger group again than just these affine matrices, but these affine matrices are inside it, so they form a subgroup in that and they stay within their group. Okay, so again, as I say, this stuff that I'm going through here, this is mathematical formalism. It's mathematical kind of structure or scaffolding, if you want to think of it. Is it vitally important that you understand all the details of this? Probably not. But just get a sense of it, that it's just, there are a set of rules associated with these things, and if you come across them, this is what we mean by it. Okay? And it's a set of rules that helps us later on. So don't be switched off by all the maths. It's not vitally important. So we have then got a thing called the orthogonal group, which is the one that preserves the inner product. So if we multiply two vectors by each other and I get a result, and if I then do have some set of matrices that if I act on one of the vectors of the matrix and I act on the other vector, the two resultant vectors that I get, if I do the inner product of those, I end up with the exact same scalar value. Okay, so what that is a very formal way of saying that the angle between two things. So in other words, if I've got my phone here and I've got a 90-degree angle between those two things, if I do some operation, my vectors are in different places, but my angle is still the same. It's just a formal way of stating that. Not just my angle, but also the lengths of them are still the same. It preserves both of those. So the set of all orthogonal matrices form the orthogonal group, which is a subgroup of the general linear group. And for the orthogonal matrix or, we have Rx or Y. This is again just proving this. What it's saying is that if I do a rotation on X and a rotation on Y, what would happen if I was to do the inner product of those is that I would end up with the X here and the Y there, and in between I have R transpose R. Now, I said to you earlier that R transpose R, the transpose of a rotation matrix is its inverse, so if I do that, I actually just cancel them out. Okay, so what I'm really doing there is I'm going to cancel those out, and I've ended up back with X transpose Y, which is of course the very definition of the inner product of these things. Okay, so what it's basically saying is that if I rotate both vectors and I've obeyed all these rules, it won't affect the inner product of the vectors. Again, mathematical formalism, we've already discussed that if I do a rotation on something, it preserves all those things, and you trusted me on that, okay? But if it came to, if you can imagine a child is going to say, but why, but why, but why, but why, and you keep having to give a further explanation, this is what this proves. In other words, that you can go right down through this and say, well, no, this is definitely the case. How do I prove that the angles will always stay the same forever for every different type of rotation I do? Here's how you prove it, and here's how you go down through the list, okay? So the orthogonal group here, as we have at the bottom, is a member of the general linear group, and also it's if I do R transpose by R, I end up with the identity matrix. Okay, so in other words, the transpose is the same as the inverse. The above identity shows that any orthogonal matrix R, we have a determinant equal to, well, if I do R transpose R, that's the same as the determinant of R squared, which is the determinant of the identity, which is a value of 1. The trouble is, if I get this, if I want to find the determinant of just R on its own, I'd have to get the square root of 1. And the square root of 1 has two possible values, it's plus and minus 1. So the thing is that if we have a set of orthogonal matrices, if I have an orthogonal matrix that can give me a determinant of -1, what I have is a situation there where I'm going to take this phone and I'm in some way, don't ask me how, I'm in some way going to mirror it. Okay, now I only have to mirror it along one axis, but I physically can't do that because it is a rigid body. I can't do that. So clearly we have to have a smaller set subgroup which can only have determinants of +1. Okay, so these are called the special orthogonal group. So they're inside the orthogonal group. The orthogonal group does allow for mirroring. The special orthogonal group does not. It's a subgroup within that, and it won't. If you do any manipulations on the matrices that have a determinant of +1, you can multiply them by each other. You will never end up with a determinant of -1 from that. However, if you do the same isn't true for the -1 case, because if you multiply two of them together that both have a determinant of -1, you'll end up with a determinant of +1. So it's not true the other way around. So in particular, SO3. Okay, so you now see that I'm using, rather than n, I'm using a 3 here. This is the group of all three-dimensional rotational matrices. Okay, so all I'm really saying here again is that within computer vision we talk about rotations, and if you're doing robotics you'll probably talk about rotations as well. They pop up in a load of different places. Because we use a three-dimensional world, we assume that we're going to have rotations in 3 dimensions. But do remember that in mathematical formalism, that is just one of the groups of the many that fall into these special orthogonal groups. And if a mathematician wants to think about things in 15 dimensions, their n is a value of 15, there's nothing to stop them doing that. And that could be useful somewhere else down the road. We don't always just deal with the 3D world. Okay. Now there's a Euclidean transformation, so you'll see there's a lot of these, but on the final slide and the next slide I'll show you how they all fit inside each other. So a Euclidean transformation L from Rn to Rn, that's just the same as we showed earlier, is defined by an orthogonal matrix or in the orthogonal group, and a vector T in which is just in Rn. So again, we want to be able to not just do rotations here but move things. So again, what we can do is we can set up a Euclidean group where we deal with homogeneous coordinates, where we do our we do this. I think I've made a mistake there. That's not supposed to be A, it's supposed to be OR. Apologies for that. It's OR. So what we have here then is a Euclidean group where OR is in the orthogonal group and T is a member of Rn. Okay, I'll try and fix that for the next time. So OR is in this SON, and of course if we're dealing in 3 dimensions, in SO3, and it has a determinant of +1. So this allows us to not just do rotations but do translations as well, and we would normally move that up into this homogeneous coordinates here in order to do that. So in particular, SE3 represents the rigid body motions in R3, i.e. the rotation and translation in 3 dimensions. Okay, so this is the special Euclidean group. Okay. So how do these all fit in each other? Well, the special orthogonal group is a subgroup of the orthogonal group, which is a subgroup of the general linear group. The special Euclidean group is a subset of the Euclidean group, which is a subset of the Affine group, which is a subset of the general linear group. Okay, so again, as I say, just on this, and we went through that reasonably quickly. All I'm trying to get at with this is that though this terminology will appear in different places throughout the literature, and when you see it, I want you to be able to decide whether that's something you really need to pay attention to, or whether it's something you can say, yeah, I know, that's just that formal set of rules, and if I need it, I'll go and look this up or look up some other place or not. But these things pop up quite a lot, and the reason is that what we talk about in terms of our specific application, when it's discussed in some wider text like a mathematical text, it has a we're generally only dealing with one special case of something that's much more general, and that's why it's good to be just aware of the terminology that's used there, because you don't know where some piece of literature is going to refer to this, refer to the mathematical rules associated with that, and you're going to be left all at sea. Okay, so again, we'll take a quick break there, guys, maybe 5 minutes, and then we'll start on the next section.